on sketching high-dimensional data.
Very great. Can you hear me? Very great. So today is the final lecture, and I'm going to focus today on dimensionality reduction, especially things related to the Johnson-Lewis-Strauss lemma. So what I'm going to focus on is the following. We have, a collection of high-dimensional vectors in some normed space. Let's say x1 up to x n in RD. Think of D as large. And we want to find an embedding. Let's call these actually vectors. This set is capital X. We want to find an embedding F into a simpler space. And for us, simpler is just going to mean, lower dimensional. So such that the geometric structure is approximately preserved. So such that, let's say, for all x and y in capital X, if you like the distance between x and y, that's similar to the distance between f of x and f of y. Okay. So dimensionality reduction here is just kind of one approach in a larger family of approaches of using metric embeddings to embed harder geometric problems into simpler geometric problems. Here it's getting simpler because we're reducing the dimension. Hopefully that makes our algorithms faster, or it makes our memory consumption lower, et cetera. But this kind of approach is more general, where it might not be about dimension. It might be about just embedding into a different normed space that's easier. So maybe your computational problem is hard in the original norm, but you can embed into some norm that is easier to work with algorithmically, right? But here we're going to focus on the case where this easier norm is just, let's say, a lower dimensional version of the original one. And kind of one of the cornerstone results in this area is a theorem by Johnson-Lewis-Strauss. Which says that, for all such x, where x has some, finite size, and for all epsilon in 0, 1, there exists an f from x to Rm, where m is 1 over epsilon squared log n, such that for all points in the point set, you have that the distances after the embedding are similar to before the embedding, multiplicatively. In Euclideans, you're looking at Euclidean norms specifically. Okay. And we do know that this bound is optimal. There exists point sets requiring, say the min, let's say 1 over epsilon squared log n dimension. As long as, epsilon is not too small. This was something I showed with Casper Green-Larson 3 years ago. one, I'm sure many of you have seen this. Some of you maybe not. And if you haven't seen it, a natural question is why Euclidean norm? Why not other norms? I don't want to spend too much time on that, but that is something people have studied. People have studied dimensionality reduction for other norms as well. And the results just aren't as drastic. Here, any endpoint subset of Euclidean space can be represented in dimension n-1, right? Because you can translate so one of the points is 0, and then now these endpoints span in at most n-1 dimensional subspace. So you can embed it isometrically in dimension n-1. And from dimension n-1, we're going down to dimension log n, right? So we get this exponential improvement in dimension, and we're still approximately preserving the Euclidean geometry. And it just turns out that, for other norms, you don't get as drastic an improvement in the dimension. For example, for L1, if you want to represent an endpoint subset of L1 isometrically, you need dimension in up to n choose 2, roughly n squared. Whereas if you want to multiplicatively approximate original L1 distances, then we can get down to dimension that's like n. So you get to square root your dimension. You don't get an exponential improvement, right? And there was, maybe I'll just cite one paper on this by so theorem, and I'm not going to state the exact theorem, but it's by let's say Johnson and Naor. Which says that if a norm space has the property that all endpoint subsets, this is for all n, such that for all n and for all endpoint subsets x embeds into an O of log n dimensional subspace with constant distortion, then that norm space is almost Euclidean. And what is almost Euclidean in their theorem? So I didn't state the full theorem, so you could say this is a high-level version of their theorem. What does it mean almost Euclidean? It means that any finite dimensional subspace of that norm space, let's say any k-dimensional subspace of that norm space, embeds into Euclidean space with low distortion. Specifically, the distortion that they proved was something like 2 to the 2 to the log star k. But it's some slow growing function of k. Okay, so what the theorem says is that kind of the only norm space that, any norm space that has this jail-like property is a norm space that's almost Euclidean for some definition of almost Euclidean. So we're going to focus on Euclidean space. It's the one, it's the space that kind of has the best dimensionality reduction. Okay, any question? John, you look like you had a question.
Yeah, can you explain a little bit intuition why this is the case?
Oh, for their
the theorem, yeah, just the
yeah, that's a good. I don't. No, I'm not. I would say I'm not. I don't have a good. I personally don't have a good answer for that. Johnson and Naor might, but I'm not sure.
Well, then maybe if you can tell us why Ly is so bad, that could also help a bit.
Oh, you mean why?
You said Ly, you can only get a root extra root.
Yeah, the best upper bound. So yeah, so there's actually for L1 we don't have a tight answer. So for the best upper bound is basically if you want 1 plus epsilon distortion, you can go from dimension n squared, n choose 2, down to dimension roughly n over epsilon squared. But the lower bounds, the lower bound there is something like n to the 1 minus O of, I think, 1 over log 1 over epsilon, something like that. You need dimension at least to get distortion 1 plus epsilon.
Is the instance of this half set points explicit?
Yeah, it is explicit. It's some recursively defined variant of the diamond graph. So I mean, I think it's something like, you know, the very first lower bound for L1 was, you know, that was, I think, by Brinkman and Charikar. I forget the year, but the very first lower bound, basically you start with a graph that looks like this, and then you kind of, I think it's something like, you know, for each edge, you recursively like change the edge into itself a diamond or something like that, and you do that some, you know, logarithmic number of times, and then as you do it, you know, you assign coordinates to these points, and then you get some L1 metric, and you prove that kind of the that thing itself has some distortion lower bound, or some dimension lower bound if you want to get low distortion. But I mean, I think that, you know, and this one, which came later, I think if I remember correctly, the construction is quite similar. It's just instead of a 4 cycle, you replace it with a longer cycle. But yeah, I mean, I don't want to get into any of this today. Okay. Yeah, so what else did I, yeah, so, okay, so let's focus on Euclidean space. So the original proof, well, actually, you know, all proofs first prove the following lemma. Which says, you know, for all epsilon and delta in the interval from 0 to 1/2, there exists a distribution over matrices, you know, and for all d, such that for any vector, if you pick a random matrix according to this distribution, the probability that that matrix doesn't preserve that vector in L2 norm is at most delta. Okay, and you know, the original JL proof, d epsilon delta was, you know, a scaled projection onto a random m-dimensional subspace of RD. But you know, there's been, and we'll talk about that, there's been kind of more work in devising other distributions that give the same result. And you know, once you have the lemma, so the lemma, why does the lemma imply the JL lemma? You just set delta to be less than 1 over n choose 2, and then union bound over all vectors x of the form x1 minus x2, where x1 and x, or xi minus xj, sorry, where xi and xj are in this capital X, right? So, oh, and I should have said here, right, what is m? M is 1 over epsilon squared log 1 over delta. Right here. So, right, so because you're setting delta to be less than 1 over n choose 2, log 1 over delta is log n, so you get the JL lemma. Now, today, what I want to talk about, we have limited time here. I want to talk about, improving aspects of JL and also applications. Okay. So first, let's do improvements. So one of them is, let's say, runtime. So why might you want to do dimensionality reduction? As I mentioned, you have some high dimensional computational geometry problem like clustering or nearest neighbor search or whatever. And whatever your algorithm or data structures, complexity, its runtime, its memory consumption, whatever, depends on the dimension in some way. And the higher the dimension, the more resources your algorithm needs to use. So if I can first, as a pre-processing step, reduce the dimension of my input and then run my algorithm, presumably my algorithm now uses fewer resources because it's working on a lower dimensional problem. Okay. So right there, so let's say the resource I'm concerned with is time, for example. So there are two steps to this. One is the time it takes to do the dimensionality reduction, and the other is the time it takes to now solve the lower dimensional problem. So for the latter, the lower the dimension, the better, presumably, right? Because if I get in lower dimension, my algorithm now runs faster. But what about the former? What about the time it takes to actually do the dimension reduction? Okay. So for that, I want to have an embedding that's fast. So the original JL projected data onto a random, m-dimensional subspace. So some vector x gets mapped to pi x, where this pi is this random projection. How do you get a matrix pi that's a random projection? Well, you need to get basically a random orthonormal basis, right? That's one way. So how am I going to do that? Here's me forming a matrix. So here I'll just pick a random Gaussian vector and then I'll normalize it. And then here I'll pick another Gaussian vector and then I'll remove the projection onto G1, right? And then now I have a uniformly random, and normalize it. And now I have a uniformly random vector that's orthogonal to G1. And then similarly, I get G3. I remove the projections onto G1 and G2 onto the span of the previous stuff, and then I normalize it, etc. Right? So basically, I just pick a Gaussian matrix and do Gram-Schmidt, right? And then the projection is then, let's say pi is then AA transpose, right? That's my projection onto a random subspace. So this, well, actually, I guess I can even, something like that. So the point is, this is a dense random matrix. Actually, I don't even need to do, I can just, yeah. Oh, okay, that's fine.
So I can ask a question?
Yeah.
So you're doing Gram-Schmidt on the columns, but you've got more columns than rows. So eventually,
yeah. So I realize this picture is is not the right picture. So let's see. So is this what I want? No. It's exactly, that's exactly right. It's exactly the other way around, right? So the point is I'm projecting to a lower dimensional subspace, right? So okay. There. Now I'm happy with this picture. Okay. Right. So I want to pick an m-dimensional subspace out of d dimensions. So this thing is d, and this is m. But in fact, now I can even just set pi to be basically A transpose, and that's fine. That works. Okay. Okay. So anyway, the point is that this is a dense, what don't I like about this? I don't like that this is a dense random matrix. In particular, I don't like the word dense here because dense means that to do this mapping, x gets mapped to pi x is going to be slow, right? So this is something that people have studied, basically how to come up with a distribution that satisfies, that gives you JL, but is faster. And kind of the history on that is, first there was Oculiotis. And what he said was, pick a matrix pi that each entry is, plus minus 1 over root m, or actually just say plus minus 1 over some scale factor. Let's not focus on the scale factor. And then what you do is then for each entry, zero it out with probability 2/3. Okay. So what he was able to show is that, of course, after you do this, 2/3 of the matrix is 0. So it's sparser. It's only 1/3 of the matrix is non-zero. And what he was able to show was he could get the same exact M that people were able to get in previous analyses, the same target dimension, even up to the constant factor, not just asymptotically, not just in big O, with this sparser construction. So, you expect now that you can embed things 3 times faster because only 1/3 of the matrix is non-zero. Then the first work that got some asymptotic improvement was by Ilone and Chazelle, and this was in 2006. And their idea was, why don't we choose pi to just be a sampling matrix? So ideally, we would, it would look something like this. Each entry would have a 1 in a random location, with some scale factor. In fact, the scale factor would just be root m. Actually, sorry, this is the transpose of what I wanted, I realize. So what I want is that every row has a 1 in a random location. And then 0s everywhere else. So this is a sampling matrix, right? So if I multiply this by some high dimensional vector x, then each entry in pi x is just a random or uniformly random sample from x. And it's not hard to verify that the expectation of pi x L2 norm squared is x L2 norm squared. So this gives you the right thing in expectation, right? But remember that other lemma that we use to get JL says we don't just want expectation, we want that the probability that pi x, is too large. Pi x L2 norm squared minus x L2 norm squared is large. We want this to be small, at most delta, right? So we don't just want to reason about the expectation. We want to bound on the probability of deviation. And the problem with this is the variance could be terrible, even though the expectation is correct, right? Because imagine that x has all its mass in one location and then 0s everywhere else. Then the variance from sampling is terrible. You're not even going to see the weight unless you take d samples, right, in expectation. So the way that Ilone and Chazelle fixed this was to basically do some kind of preconditioning to x. The idea is pi will actually be the product of a few matrices. And the first matrices their job is just to precondition x to make sure that the mass is well spread. And then the final matrix will be the actual sampling, because once it's well spread, sampling works, right? If x had been, let's say, 1 everywhere, for example, then sampling has no variance. So their idea was to use the uncertainty principle, which says that both a vector and its Fourier transform can't both be well concentrated. Okay. Unfortunately, this doesn't quite work either. If so you could say, well, why don't I just now do pi is a sampling matrix times the discrete Fourier transform, right? So, there are 2 things that are wrong here. There's one main thing that's wrong, and then you'll see that it's not so, it's okay. So what's wrong here? What's wrong here is that, what if we have the opposite situation where x is actually very concentrated? Now you apply f. Now after you apply f, it's collapsed all its mass into one coordinate or a few coordinates. Now sampling doesn't work. So you have the opposite problem now, where your original vector might have been dense, and then after you apply the discrete Fourier transform, it's sparse. But it's not really just one or the other. You can construct examples where a vector and its Fourier transform are both, evenly spread on root D coordinates. Okay, so kind of neither the vector nor its Fourier transform is particularly well spread. Okay, so what they did do instead was they actually put another matrix here in the middle, so now their construction looks something like this. This is the DFT, actually not here, sorry, here. Okay, so here's your DFT, your discrete Fourier transform. This is F, and then you have this diagonal matrix D, which has plus minus ones on the diagonal, and then now here you have your sampling matrix, and then you have some scale factor. Okay, and now this is pi. And what they're able to show is that kind of if you call this matrix A, which is the product of these two matrices, then they can say that for all x, the probability that if you look at the ratio of the L infinity norm of AX to its L2 norm, by the way, the L2 norm of AX is just the same as the L2 norm of X, right? Because D and F are both isometries. The probability that this thing is large is small. So with high probability, you do get kind of a well-spread vector where the definition of spread here is looking at the ratio of the L infinity norm to the L2 norm. And then now that you have a good spread, you can sample. Okay. And they got a good result here, which eventually led to basically M being so if you want the optimal M, 1 over epsilon squared log n, then unfortunately, even though you get a pretty decent spread here, you don't get it perfectly well spread. So sampling doesn't quite work perfectly. So you do need to oversample compared to the JL bound. But one way to fix that is to then here at the very end, let me actually put it here. Still getting used to changing to eraser on it. There we go. So here you could put, for example, a slow JL matrix, like random projection or something, and then set pi to be this. And maybe I should make it clear now that kind of sampling is getting you part of the way there, but it's not as good as you want. So you're able to reduce the dimension a lot using sampling, but not to the optimal bound. And then you wrap it up at the end by doing a slow JL down to the optimal bound. There's an optimization they do in their paper that's a little bit faster than this, but in particular, instead of a sampling matrix, they just use kind of a random sparse matrix. But qualitatively, it's quite similar. And what you'll get is M being the right thing. And embedding time to map X to pi X is now something like D log D to do the fast Fourier transform plus some M cubed. And this M cubed is basically coming from the fact that since sampling doesn't work optimally, you have to do this slow JL at the end. So that's giving you an additive M cubed. Okay, so there's been a bunch of work that I'm not, I have limited time. I don't want to get into all of it, but the bound's been improved to M squared. It was improved to M squared by Alone and Liberty. And then there was a conceptual shift that was kind of first it was, not completely crisp, but it was there in Alone and Liberty in 2011. But Kramer and Ward really made it apparent, which is here we said, first condition on F times, let's call it, this was D. First, we condition on F times D being good. Good meaning it spreads the mass, around in X. We condition on that good event. And then once you condition on that good event, sampling works with high probability. And Kramer and Ward and Alone and Liberty in 2011 had this kind of conceptual, or maybe it was 2010, had this conceptual shift where actually what you want to do is instead you condition on S times F being good for some definition of good. Okay. And then once S times F has that good property, then D gives you a good JL distribution when you throw D on top of it. And their definition of good was that S times F satisfies what's called the restricted isometry property from compressed sensing, which I'm not going to get into right now, but you can get some better bounds that way for the JL problem. Okay. So anyway, this was one approach. This was the Illoan and Giselle approach. And then another approach is to sparsify pi. So going back to Oculiotis's approach in 2001 of making a third of the entries non-zero and zeroing out 2/3 of the entries. And here, what was eventually, so this was, Oculiotis studied this in 2001, and then there was Dasgupta, Kumar, and Sarlosh in 2010, who they were the first to show that you can get actually some asymptotic improvement, not just a factor of 3. And then, kind of the state of the art bound now is due to myself and Daniel Kane in 2012. And what we show is that actually the count sketch, for example, gives a nearly optimal bound. So remember, what is the count sketch? We talked about it at the end of last lecture, or was it, or not the very end, but near the end, when we were talking about the frequent items problem in data streams. Okay. So here, what does pi look like? Remember, like the rows were divided into these blocks. So, and if you look at a column, kind of in each entry, we picked a random location chosen by a hash function. We made that entry be ±1, and then the rest of the column was 0. And then in this one, we chose a random location. We made it ±1. The rest of that column is 0. Okay. So let's say we have S blocks, which means S non-zeros per column. And the total number of rows here is again M. And we're going to shoot for S being a little low of M. Okay. So we're actually going to get an asymptotically sparse matrix. And the theorem is that if you pick M to be 1/epsilon² log n, which is the JL bound, you can choose S to be only epsilon times M. Okay. So you can get an asymptotically sparser matrix. And furthermore, this is actually optimal up to a log 1/epsilon factor in S. So there exist point sets where if you insist on having target dimension meeting the JL bound, 1/epsilon² log n, via a linear map, then the column-wise sparsity of that map has to be at least epsilon m divided by log 1/epsilon. And this proof was due to myself and Hui Wen. Okay. So if there are no questions about this, I want to move to applications. So the first one, I'm going to focus mostly on two. And one, I want to talk about Kmeans clustering. And two, I want to talk about randomized linear algebra. So let's say clustering. Okay. So you have a bunch of points in high dimensional space. Okay, so let me try and cluster them. And I want to find, some cluster. I'm given some parameter k. And I would like to find k clusters So for example, let's say here now k is 3. I would like to find kind of the best choice of 3 clusters possible for this data. And what does best mean? It depends on some objective function. But here maybe this is one cluster, this is another one, and maybe this is, unfortunately there's that outlier, but he has to go somewhere. Okay. And K-means clustering is the goal really here is to find cluster centers y1 up to yk. Oops. Okay. And these don't need to be in the original input. To minimize the sum I goes from 1 to n of the min j goes from 1 to k of xi minus yj L2 norm squared. So this is the K-means clustering problem. Okay. And this is an NP hard problem, but there are heuristics that are common, like Lloyd's algorithm. Okay. And as you might imagine, algorithms for this problem have runtimes that depend on dimension. Okay. So, can we speed it up using random projection? And the answer is yes. And the first, so let me write that objective function again. So we said the sum I goes from 1 to n. The min j goes from 1 to k of xi minus yj squared. We want to minimize this over choices of y1 to yk. And one claim is that once you choose the y's, so let's say going back to that picture, so you have a bunch of points here, you have a bunch of points here, you have some points here, and then now you have these clusters. What are these clusters? These clusters are just basically, I'm partitioning the points according to the y's. So the first cluster is all the points which are closest to y1. The second cluster is all the points which are closest to y2. The third cluster is the closest to y3. So the y's are somewhere in here. So like y1 is here, y2 is here, and y3 is here. Okay. So now you could say, look, instead of just choosing the y's, why don't I choose the partition, and then choose the y's inside each partition. Okay. That's so like, I could basically have min over partitions, then min over y into partitions, etc. That's going to give me the same exact objective if I choose optimally. But now you can analyze this and say, look, once I choose the partitions, there's actually a closed form solution for what the optimal y is for that partition. So, if you fix partition P, which is P1 up to Pk, then the optimal choice of yi for pi is just the centroid of the points in that partition. So it's 1 over the size of pi, the sum over, let's say, I prime in pi of xi prime, right? It's just the centroid. And if you use that fact, you can then rewrite the objective function to say that the cost of a partition with some simple manipulations turns out to be the sum j goes from 1 to k of 1 over the size of pj, sum over I less than I prime in pj of xi minus xi prime L2 norm squared. Okay, so this, you can prove that this identity holds. And what this says is that the cost function now is a linear combination of square distances between points in the original data set. And the coefficients in this linear combination are all non-negative. Okay, which means that if I'm able to approximate all these distances by 1 plus or minus epsilon, then the entire cost is approximated up to 1 plus or minus epsilon. So this implies that 1 plus epsilon distortion embedding of the xi's preserves the cost of any clustering, any partition up to 1 plus epsilon. Okay, so I can get such an embedding, do JL on the points, and now cluster the lower dimensional versions of the points, and I'll still have a nearly optimal clustering for the original point set. So this implies I can cluster in dimension only kind of 1 over epsilon squared log n, and still get a good clustering. Okay. I see an open question from Arnold about p-stable sketches. I'm guessing that's old.
There is a question on whether if you're in the LP space, whether you can use the p-stable distribution variables to do the projection. And Joe answered that the concentration is a property, and this is additional remark to that.
Oh, right, yeah. The concentrate, yeah, right. So these Gaussian random variables or plus minus ones are they're sub-Gaussian. They have very good tail bounds, but that's right. For p-stable, the tail bounds are really bad. Right, and as I guess maybe Arnold was pointing out, if you do a median is not an embedding into LP if your estimator is a median, right? So.
But if your purpose is to actually, for data storage, just to more efficiently store the distance, maybe you can repeat the sketching for a number of times, so then you get actually a good.
Right. So yeah. So this is a good point. If all you care about is a data structure that lets you recover distances, right? That's different than wanting an embedding into L2. Now, specifically for Euclidean space, we do know we have for example, so there's a paper by Jerem and Woodruff in 2011 that looks at the question of just sketching for LP, right? Where you want to be able to, you want 1 plus epsilon approximation to the norm with probability 1 minus delta. And you don't care that it's an embedding. You're allowed to sketch however you want into some data structure. And for that, they can show that you can actually get a lower bound that's, again, 1 over epsilon squared times log n, just like basically the kind of, or yeah, basically you'll get a lower bound that's like basically saying that it's similar to JL. Now, there's another related problem, which is dot products. Let's say that I have a collection of unit norm vectors, and I want a data structure. Let's say these are points x1 to xn. They all have norm at most 1. I want to build a data structure so that later anyone says query ij, I'll return to them an additive epsilon approximation to the dot product between xi and xj. Okay. Now, if I do JL and then round the target vectors, that will let me recover dot products, because I know that xi minus xj L2 norm squared is equal to xi L2 norm squared plus xj L2 norm squared plus twice the dot product, right? So moving this around, this is saying that xi dot xj is equal to, and let's say they're unit norm vectors, this is equal to 1/2 2 minus xi minus xj L2 norm squared. Okay, so if I'm able to approximate the L2 distances, which I can get from JL, I can estimate the dot products. Okay, so I can use JL to do this. It turns out that for that problem, JL is actually suboptimal by a log factor, and it's known what the optimal data structure is, and that was something that was done by Alone and Klartag. Okay, in 2017. And actually, even for, okay, so I realize now for, even if you want a multiplicative approximation to the distance, JL actually has, just for the data structural problem, like again, the same setup. You have n vectors, x1 up to xn. And when someone says query ij, you need to return a 1 plus epsilon approximation to the L2 distance between xi and xj. Actually, for that, just doing JL and storing the target vectors is not optimal. There's something better you can do, and that was shown by Indic and Wagner, Tal Wagner. And I think Tal is actually one of the participants. Is he? No, he's not. I'm not sure if he's here in the program, but okay. And I forget the year for that. But in some, I mean, there are models where JL is optimal. Like in the streaming model, if you're streaming a vector and then you want to know its L2 norm at query time with probability 1 minus delta, you want a 1 plus epsilon approximation. This JRAM Woodruff paper from 2011 does prove that the bound you get from JL is an optimal bound. Okay. So that's aside from just embedding. That's kind of any sketching procedure in the stream. So this is for multiplicative. Oops. Multiplicative approximation to the distances, and then this is additive to the dot products. Okay, so let me go back anyway to clustering. There's more I want to say. Now, let's say that I have my points. Actually, let's do the following. So let's say I have 4 points. And I colored them according to the partitions they're in. So there are 2 red points, 1 gray-blue point, and 1 yellow point. And there are 3 partitions and 4 points. I can write a matrix now, which looks as follows. And let's say that these are points. These are points 1, 2, 3, and 4. I can write a matrix for this corresponding partition that looks like this. The number of rows is 4 because there are 4 points. The number of columns is 3 because there are 3 sets in the partition. What's in partition 1, the red partition? Points 1 and 3. So I'll put a 1 over root 2 here, 0, 1 over root 2, and a 0. Why root 2? Why 2? 2 is the size of the partition. There are 2 points in this partition. That's why it's 2, root 2. And then point 2 is in partition 2, so there's a 1 there. And then point 4 is in partition 3, so there's a 1 in the 4th row. Okay. And then I can also define a matrix A, which is the data matrix, where basically there's x1, x2 as rows up to x4 here. Okay. And it's a calculation, but I promise you it's true. If you look at, first of all, what can you tell me about XP? It has orthonormal columns. So XP transpose is an orthogonal projection. And if you look at XP transpose applied to the matrix A, it basically replaces each row of A with the centroid of its partition. So then if you look at A minus XP transpose A, each row of that is the original point minus the centroid of its partition. So it's exactly the difference vector between that xi and the corresponding yj, the yj for its partition. So if you look at the Frobenius norm squared of this matrix, this is just equal to the cost of the partition. Which means that you can rewrite Kmeans clustering as, compute the min over all partitions P of the Frobenius norm of identity minus XP transpose A Frobenius norm squared. And let me just call this, which I'll just rewrite as the min over all Q in a certain set I'll give you a name. Right, where let's say the rank of Q is also at most K. So it's some kind of constrained low rank approximation problem, right? Basically, I'm saying that Q has to have low rank, but in addition, it's not just an arbitrary low rank matrix. It's a low rank matrix that has to be of the form XP transpose, where P is a partition. Okay, so it's some kind of constrained low rank approximation problem, and what this paper was able to show, so this is due to Cohen, Elder, Musco, and Persu, I think it was 2015, is that if instead you minimize identity minus Q A pi transpose Frobenius norm squared, right? So pi is this like JL kind of matrix, right? Then the Q you'll get will give you the optimal value up to 1 plus epsilon, as long as pi, as long as pi has enough rows in it. So if you have your target dimension M being something like K over epsilon squared, then it'll allow you to, approximately solve any constrained low rank approximation problem, including Kmeans clustering, which is just a special case of a low rank approximation constrained low rank approximation problem. So this K is the number of partitions, right? You want to find K clusters. So it's completely independent of N. JL gave you a bound of log N. Here they got a bound of K, which is independent of N. And actually more recently, it was shown by Makarichev, and Rosenstein in 2019, that actually you can get log K okay. So kind of that's and that's almost optimal. There's a log K. The lower bound is that you need log K over epsilon squared. So up to that epsilon inside the log, it's optimal. So kind of there's an example of random projection in action, and if you just naively use a JL bound, you'll get something. But if you tailor the analysis to your problem, in this case clustering, you can get something that's even better. And the final thing that I want to show you was that final application was randomized linear algebra. So, one of the things is approximate matrix multiplication. And I'll say something about that. Least squares regression. I'll say something about that. And I won't have time, but you can also use this for a bunch of other problems as well, such as approximate low rank approximation, or a constrained case as well, leverage scores estimation. Column subset selection. And I suggest one of the things you can look at is there's a book called Sketching as a Tool for, I think, maybe numerical linear algebra. And this is by Woodruff. You can take a look there. So approximate matrix multiplication, what's the idea there? The idea there is, I want to compute, so I have a big matrix. I have two big matrices, A and B. So let's say A is a matrix which is, let's say, A by N, and B is a matrix which is B by N, or N by B. Is this what I want to do? Actually, let me change this up a little bit. Okay, and I want A transpose B. So naively, this would take time, which is like A times B times N time. But instead what I do is I compute pi A, and I compute pi B, and I compute pi A transpose pi B. Right. And I would like to argue that that is close to A transpose B. So I would like that, for example, pi is a random matrix, so the probability over pi that pi A transpose pi B minus the truth, which is A transpose B. The probability that this is large is small. Let's say small means delta, large means going to mean something like epsilon times the norm of A times the norm of B. And people have studied it also with other norms like operator norm. But you can show that, if you just basically pick pi to be a random projection matrix, like a JL matrix, you'll get this kind of guarantee. And, you can basically pick M to be something like 1 over epsilon squared times log of 1 over delta. Okay, that's your target dimension. So now pi A and pi B are smaller matrices. Think of N as huge, right? So remember A and B, they're huge matrices. So, they have a lot of rows, let's say. So pi A has many fewer rows. They can have different number of columns, but they have a lot of rows. Okay. And actually, aside from JL, another thing you could do is sample. So you can actually choose pi to be a sampling matrix where the probability that you keep the ith row of A is proportional to something like, I think, the L2 squared of the row. And if you do something like that, you can get a similar kind of guarantee. And then regression. So you want to minimize, let's say now, x beta minus y, where I'm looking at the case where x is a really tall and skinny matrix. And instead what you do, so this is beta ls, this is the least square solution. So that's the argument, I guess, over beta. So instead we just compute beta tilde ls, which is the argument of pi x beta minus pi y. Right. And you want to argue that this beta tilde is approximately optimal. And that's something you can do as well with there are sampling approaches. I want to say a word about that, but also using kind of random projection approaches. And the key thing there, it turns out to be that you want what's called the subspace embedding property. Which is, if E is a linear subspace, Oh, sorry, then we say pi is an epsilon subspace embedding for E if for all x in E, if you look at pi x L2 norm squared, it's approximately x L2 norm squared. So it's basically, JL, but where you're not doing JL on a finite set of points, you're doing it on an entire subspace. And it turns out that you can get, in this case, M to be O of the dimension of E over epsilon squared. And, claim this is called, this is part of something called the sketch and solve. So actually this here, or this idea that beta tilde is just going to be the optimal thing for the sketched version, this idea is called sketch and solve, usually in the literature. And the claim is that if you do sketch and solve, it works as long as pi is a subspace embedding. So if pi is a subspace, an epsilon subspace embedding for the span of y as well as the columns of capital X, remember we're trying to minimize x beta minus y. Then if you look at x beta tilde ls minus y, it's almost optimal. So you'll get something like this. It'll do almost as well as the true least squares optimal point theta. And this has a one-line proof, which I'm not going to do now because I don't have time. But sketch and solve, and actually there are other ways of arguing this as well. So there's another. It's actually also possible. Can also show, this is in Charles's paper. Charles's paper can also show that M being O of so what does this give you, by the way? So the dimension here, the dimension of E in this case is going to be basically D plus 1, right? Because the input matrix X has at most D columns, and then Y is one more vector. So this says that you can map down to dimension D, roughly D over epsilon squared instead of your original dimension, which was N. You can also show that, in fact, in this case, that D over epsilon works. And there's actually another argument that uses subspace embeddings in a different way, where you can actually end up working over dimension D, O of D, independent of epsilon, via an iterative approach. So basically, you use a subspace embedding as a way to find a good preconditioner for the matrix, to find a new matrix with the same column space, but with better condition number. And then you run gradient descent with that matrix. And you can show that you only need something like log 1 over epsilon iterations of gradient descent to get good error. And you're only ever working over dimension D without the poly 1 over epsilon dependence. Okay. So that's another thing you can get. And maybe the very last thing that I want to show, like slide that I'm going to write anything on, is this one. How do you get a subspace embedding? So one way is you do kind of JL over a net of the subspace. But this is not always, doesn't always give optimal results. For example, if you remember with sparse JL, I said that you get M to be 1 over epsilon squared log N, and S to be O of epsilon M. This would lead to, in this case, for subspace embeddings, M to be O of D over epsilon squared, and S to be O of D over epsilon. But in fact, if you were to analyze sparse JL specifically for the purpose of getting a subspace embedding, like, for this random matrix, what S and M do I need to get a subspace embedding? You can actually get an exponentially better bound in S. The truth is that this D can be replaced by something like, log D. And, but at the cost of, you will get like some log D here as well. So the kind of the tightest analysis here is due to Michael Cohen. But there's been, there's other work on this kind of before Cohen as well. So the first paper to show that you can get a really, really sparse subspace embedding was by Clarkson and Woodruff in 2013. Then there were a series of papers afterward that kind of got better and better bounds. And down that line, the one that has the best bound is due to Cohen. And also even the case for kind of this Fourier transform approach of Eilon and Chazelle, rather than apply the JL results from that and apply it to a net to get subspace embeddings, if you directly analyze that construction for subspace embeddings, you can get a better bound as well. There's a lot to tell you. Unfortunately, we're out of time. I am teaching this course. So if you go to sketching bigdata.org/fall20, that's a course that I'm teaching this semester on sketching. It's Mondays and Wednesdays, 1:30 to 3 p.m. Pacific time. So actually the first lecture is in 25 minutes. Unfortunately, there is a cap on how many people can participate. So it's open to all UC Berkeley folks, but for people in the program, if you're a long-term participant, then please join in. I'm happy for you to join in, but it is a class. It's not open to the entire world, unfortunately. Yes. So that's all. Any questions?
Any questions? Maybe I have a sort of naive question. In the subspace embedding, is the point that the matrix pi should be constructed without looking at the subspace?
So should pi be constructed without looking at the subspace? So that's what's called oblivious subspace embedding.
But I'm a bit puzzled. You can look at the space. You are embedding the space of dimension d to something of larger dimension.
Yeah. So okay. So good. So here's so good point. If I'm allowed to actually, so how is the subspace usually given as input to me? It's usually given as like the column space of a matrix. Okay. So I imagine that there's some matrix A which looks like this. So I know that it has its column space has low dimension. Okay. Now I want to find a subspace embedding pi such that pi A has roughly the same. I want to say that I want to find a good subspace embedding for the column space of A. So basically, I want that for all x, pi AX has roughly the same norm as AX. Now, if I'm given the matrix, I could of course find a perfect subspace embedding. I can just say, look, to compute the SVD, A is equal to U sigma V transpose. Okay. And then I think what I want to do is I want to pick, let's see, so pi AX. I can just pick pi to be U transpose. If I pick pi to be U transpose, then actually, not only do I get that these things are, approximately equal. How do I, oh, here we go. I actually get equality, right? I actually get that pi x equals AX if pi is U transpose. The problem is that it's going to be very expensive for me to get this pi because I have to compute the SVD, right? For example, I might, for regression, that, getting this SVD is like just as expensive as actually solving the original regression problem. So I haven't gained anything. Now, it's, so yes, one advantage of obliviously getting the pi is that there's no computation time to get the pi, right? Because I don't have to look at A. However, there are non-oblivious methods that are also fast. One of them is leverage score sampling. So there are algorithms out there that will approximately compute what are known as leverage scores. So these are numbers associated with the rows of A. And then I sample each row in proportion to its leverage score. And it's possible to do this quickly enough that it's meaningful for applications. I didn't have time to get into leverage score sampling, but that is another non-oblivious approach.
Great. Any additional questions? Okay, then let's thank Jelani for a nice set of lectures. I think that's all for the sketching. If you need to know more, you need to go to the course, I guess.
Okay. Oh, and for those people, I guess, who want, don't want to sit in the course, but still want information from the course, there's a 2015 version that is actually all the lectures were recorded. The host is after you start. Okay, all the lectures are recorded and it's on YouTube. It's publicly available. So just basically, get rid of this fall 20. And then kind of there's a link that says, a previous version by Jelani of this course. Go there, click 2015. And in the 2015 version, you can find lecture videos. Okay.
Okay, great. That's all. We are done for today.
Okay, bye-bye.
Thank you.